Hello everyone, this is group SWML40 and we are here to present to you a dual objective machine learning approach for electronic waste readiness classification and depreciation forecasting. I'll be with my colleague Subga Ibrahim and my name is Nakalema Jibran. These are the contents of our presentation. This is what we are going to find in the presentation: problem statement, related work, dataset description, etc. So, with a background and introduction, this study addresses the limitations of fixed life cycle models by developing a machine learning framework that evaluates e-waste readiness through a multidimensional analysis of device health and historical patterns. E-waste readiness we are looking at is an electronic device such as a TV, a phone, a refrigerator ready for disposal. So we were able to get some related works and we referred to two. One, which is a predictive maintenance using machine learning. This project originates from industrial engineering and reliability theory, evolving significantly with the rise of Industry 4.0. A representative study conducted at Eastern Mediterranean University demonstrates how machine learning has been integrated into maintenance systems for industrial equipment. Then the second one is rule, which is the remaining, is full life cycle prediction. We had the problem statements, we have two, that is the domain application problem and the computational problem. With the domain application problem, the rapid growth of electronic waste has outpaced traditional manual and rule-based methods for determining device end of life. Disposal decisions depend on complex nonlinear interactions between factors such as usage factors, usage condition, value retention, and durability. Then with a computational problem, the core computational problem of this research involves developing a high-fidelity classification framework capable of mapping nonlinear multidimensional electronic device data to binary e-waste readiness state. We had research questions and objectives, and the questions are: how can EDA reveal meaningful patterns among electronic device features? Which features greatly influence the readiness of a device for disposal? What kind of machine learning models are suitable for a combination of numerical and categorical data? Our dataset has both numerical and categorical data, as we shall be seeing as we move on. What is the significance of machine learning in electronic waste management? Then the objectives, we had a main objectives, which is to analyze patterns of depreciation and usage to estimate whether a device is approaching the end of its useful life. Then the other objectives, we have to investigate life cycle indicators such as usage duration relative to expected lifespan in order to determine how device usage affects remaining value and usability. Then to engineer new features, and then to define a heuristic indicator of e-waste readiness. The contributions and outputs. Our study presents a comprehensive and practically deployable approach to electronic waste readiness classification by integrating domain-informed feature engineering, advanced gradient boosting techniques, and structured MLOP's deployment framework. MLOPs is machine learning operations. Then the research introduces a domain-driven feature engineering framework tailored specifically for electronic device lifecycle assessment. Then the study leverages the capabilities of LGBM. Our LGBM is the model that we took to construct a high-performance classification model for e-waste readiness prediction. With our study, we realized that we're having a leakage. So instead of the model being intelligent, it was actually copying patterns, and it was due to three features: that was expiry years, user lifespan, and current price. So removal of these three, as it predicts the e-waste readiness of a device, was removing the leakage, and now the model was actually being smart. Let me invite my colleague to present the methodology and system architecture.
My name is Subga Ibrahim, and I'm going to present to you the methodology and system architecture of our model. So the proposed model employs the LGBM boosting machine, and it is a highly efficient implementation of the gradient boosting decision trees designed for scalable and high performance learning on structured data. So for the first step that we did in our methodology was gradient boosting framework. So the LGBM follows an additive boosting strategy where multiple decision trees are trained sequentially, and each subsequent tree aims to minimize the residual errors of the previous ensemble. So the model prediction at each iteration T is given by, so here we are having the prediction prediction of the iteration, and we're having, which is equal to the prediction of the iteration t minus 1 plus the eta of the eta function of the iteration of x. So next we have the gradient-based one-side sample, which is GOS. So to reduce the computational complexity during training, the LGBM employs a GOS, which selectively samples data instances based on the gradient magnitude. So the adjacent information gain is computed as we can see. So the gain is 1 over n over the summation of ki plus 1 minus a over b times the summation of ki, where we're having b from I, where I is an element of b. So A is A represents the large gradient samples, B represents the sampled small gradient instances, and small a and b are the sampling ratios. So next we have the exclusive feature bundling EFB. So to handle the high dimensional sparse data efficiently, the LGBM uses the EFB, which reduces the number of features by bundling the mutually exclusive features. So if two features, xi and xg, are mutually exclusive, so the x bundle will be xi plus xg. The next one we have histogram-based sample split finding. So instead of evaluating all possible split points, the LGBM discretizes continuous features into bins and histogram. So next one we have the leafwise twist growth strategy. So unlike the traditional leafwise growth, the LGBM grows trees leafwise, selecting the leaf with the maximum split gain. So at each step, the leaf with the maximum split gain is the argument of the maximum gain of that particular leaf. So next we have the final prediction, and for the final prediction, we have a sigma function which aggregates all the outputs of the other trees. So next we have the data description and exploratory data analysis. So we had a rigorous data validation process which we conducted to ensure the viability of the EOS predictive model. So first of all, we realized that our data was complete, had no our data set was complete, had no missing values, and it was also it didn't have any duplicate detection. We didn't detect any duplicates. And on my left is the table. On the left is the table that shows the data description. So we had 10 features, and these are the data types.
The description of the features. So the product type we look at, is it a phone or a laptop? Brand, we look at, is it Dell, HP? Build quality, what is the quality of the materials that are used to make these devices? User lifespan, as a user, when I buy this device, for how long do I anticipate to use it? Then the usage pattern, am I using it at a high rate, moderate, heavy? Then with the expiry years is technical. It is determined by the technical team basing on the quality of materials they use to construct these devices. Condition, is it in good condition, bad condition? Original price, what was the price of this device when it was first released onto the market? Use duration, for how long has it been in use? Current price, what is the current price of the device?
So next we have the output results and discussions, and on the left is the summary of our metrics from the model. So the accuracy, so the LGBM achieved an overall accuracy of 90.17 and an outstanding area under curve of 0.9756, so which underscores its ability to differentiate between function and end-of-life hardware. So for the precision, we have 88.58 and the recall as 86.90, and then F1 score of 87.73. So for the visualizations, on my extreme left is a precision recall curve, and we can see that the model has a high precision until it reaches a recall of 0.6, where it starts falling. So next we have an area under curve, which is very high, 0.976, and it tells us that the model is able to capture true positives and true negatives at a high rate. So next we have the confusion matrix, which is 1650, and which is a confusion matrix, and it shows that the model is able to capture two negatives and two positives also at a high rate. So the output, we have the light GBM featuring fountains, and we can see that the product type has the highest feature importance for the LGBM model. So we can see that also the investment density ranks higher than the raw brand or condition variables, validating the hypothesis that the ratio of cost to build quality is a superior indicator of disposal necessity than price alone. So next we have the class-wise probability distribution, and we can see that we have a high density on the extreme end, which is 0 and 1, so which means that the model has a high decisive power on classifying whether a model whether a device is EOS ready or not. Next, we have the conclusion, and this study represented a robust and scalable approach to electronic waste readiness classification using an LGPM machine learning framework. So by combining the domain-informed feature engineering with advanced gradient boosting techniques, the proposed model effectively captures both behavioral and structural characteristics of electronic devices. Next, we have the anticipated limitations, and one of the anticipated limitations is data distribution drift, where incoming real-world data devices from deviating training data set due to changes in device usage patterns in data collection practices. So to address this, a continuous monitoring mechanism is incorporated within the pipeline to track input, feature distribution, and prediction confidence. So next, we have the machine learning operations, and for our front end, we deploy it on Vercel. So for this front end, the user inputs the form, which includes the values. The user includes they input the values of the features of the given device that they have to analyze, and then they can also submit. So the front end on Vercel is connected to the back end using an API. So the API resides on Hugging Face, and it receives the data, applies processing, and calls the model for prediction. So after that, we give the prediction logging, the performance monitoring, and data drift detection. Next, we have the knowledge distillation and training pipeline. So knowledge distillation is a model compression technique in which high-capacity model, the teacher, transfers its learned knowledge to a smaller and efficient model, which is the student. So the objective is to train most of the predictive performance of the teacher while significantly reduces the computational complexity and inference time. So what we are having, step 1, for our distillation pipeline, we had the teacher, which was the LGBM, which was optimized with Optuna, and next we had the ensemble. So the LGBM we combined the 10 models via majority voting, and the third we had the soft label. So the average probability outputs from the ensemble were combined, and the student model. So our student model was a neural network which was trained on both the soft and hard labels. So next we have the student training progress. So we had 150 epochs, and we had a decrease in the loss from the teacher to the student model, and our final loss was 0.4138. So the validation accuracy our final accuracy was our peak accuracy was 0.8647, which happened on epoch 110. So next we have the efficiency comparison. So the accuracy of the teacher ensemble, it had 0.903 accuracy, and the student model achieved a highest of 0.657, and we had an accuracy gap of 0.0380.
Then we have pruning. With pruning, we are trying to introduce on the complexity of the model. So we prune the LGBM. So it ensures that the model maintains high predictive power on unseen data. So it is the process of intentionally limiting the complexity of decision trees to prevent model from memorizing noise or outliers, which were identified as roughly 9.5% of our data set. So the key mechanisms here, we have the pre-pruning via max depth and architecture constraints. So with the pre-pruning, we set the max depth to 5. So with setting this maximum depth there, the model performs pre-pruning. This stops trees from creating overly specific branches that might only apply to a small number of rows in the training set. With architectural constraints, limiting num leaves ensures that the tree architecture remains shallow enough to focus on broad trends in e-waste behavior. So the pruning logic ensures that when the LGBM pruned model is saved, it remains accurate for new electronics rather than simply performing well on the existing data. So it remains accurate even with the new. So this is a deployment. This is how our interface looks like. We have now, when you're interacting, you interact with the front end. That is done. That is deployed on Vercel. But you have to ensure that your front end and the back end are connected, lest you will not get results. So we first test if it's connected, and here we can see here it is not tested, and here it shows connected. Then we input the different features we are going to consider of whatever device we are going to analyze. Then you analyze. Now this is what we got as our result. So with the device we were analyzing, it was a camera, it was an LG, yeah. So we realized that it was not ready for disposal, but in around 2032 it will be ready for disposal. So those are our references, and thank you for listening to us.